Hi, kids. I'm gonna teach you how to do a two-body problem. Why is it called a two-body problem? Well, look, I have one, two different objects. Hey, a two-body problem. In this particular case, we're gonna say that I have a flat table. There is gonna be some friction, and then I have a 5 kilogram block up here, a 2 kilogram block that's hanging. And I want to, it's starting from rest, starting from rest. Does it have to be starting from rest? No, it doesn't. Okay, but most of the time it is. We're going to find the acceleration of the system. Hopefully you understand they're attached by a string, so the acceleration of this has to be the acceleration of this, the magnitude anyway. Obviously this is going to accelerate to the right and this would accelerate down. And then we're going to find the tension in the string. Now, the other thing that we're going to assume right now that this pulley right here is not going to affect anything. So it has such an incredibly small mass compared to these things that this teeny tiny mass really is not going to affect anything. Later on, we are going to do problems where this doesn't have a small mass, but for right now, we're going to keep it simple. So that's our basic problem. It is flat like this, like this. Okay, so take a wild guess what we are going to have to do to start. Let's see. We're going to draw a picture. That's right, because in physics, you always draw a picture first. Now, here's your picture, but in this particular case, you have to draw your FBD. So if we're going to draw our FBD, we have to draw two separate FBDs, one for this one for this one. This is where I'm going to strongly recommend, let's use some colors, especially the first time through, just so that you can really see the difference between the two. So let's draw the FBD for this one. So what forces are acting on that guy? Well, it's sitting on the table. I have the normal force going up. I have the force of gravity going down. I have the force of tension, and then I have the force of friction. Now, a couple things. Let's make sure that this makes sense. These two forces are going to be the same size. Why? Because this thing is not going to accelerate into the table or magically hover off the table. This force of tension has to be bigger than this force of friction. Why? Because if I release this thing, it's not going to magically start accelerating this way. It's going to accelerate this way. Okay. So make sure you draw your FBD correctly. So that's what your FBD would look like for this guy. Since we actually, let's draw our FBD for this guy next. I'm going to use a different color for that one. Okay. So I have my 2 kilogram box, just so we are, on board here. I'm going to make that one blue, that one red. Okay. And what are the forces acting on this guy? Well, I have the force of gravity pulling it down, and then I have the tension pulling it up. Now, I didn't do a great job, which I'll explain why in just a minute, but all right, so let's talk about what I drew and why I drew it. Now, this guy is accelerating to the right. This guy has to be accelerating down because this guy can't accelerate up and this guy to the right. That doesn't make any sense. So that means that this force down has to be bigger than this force up. But if you think about Newton's third law, so let's think about Newton's third law and then we'll kind of come back to this and I'll talk about why I didn't do such a great job drawing, but that's okay. But let's take a look. I want you guys to take a look here and find all between my two FBDs, or on this FBD or on this FBD, I want you to find all of the Newton's third law pairs. So pause it, and then I want you to write down, well, this and this is a Newton's third law, this and this is a Newton's third law pair, and so on and so on. So pause it. Did you pause it? Pause it, pause it, pause it, pause it, pause it. Okay. So did you say, oh, the normal force and the force of gravity are Newton's third law pair? Did you? Well, if you did, you're wrong. Okay? Because the Newton's third law pair, remember, it's always object 1 pushes or pulls on object 2, and then object 2 pushes or pulls back on object 1. This normal force is the table pushing up on the table. This force of gravity is the Earth pulling down on the object, okay? Those are not Newton's third law pairs, okay? So are there any Newton's third law pairs? There are. Well, this force of tension and this force of tension are the Newton's third law pair. Why? Because this is the 5 kilogram mass pulling on the 2 kilogram mass, and this is the 2 kilogram mass pulling on the 5 kilogram mass. So these two forces have to be the same size, which is why I drew it the way that I did. So like the size of this force has to be the same as the size of that force. Well, here's the problem though. This guy has to accelerate down, so this force of gravity has to be bigger. Well, guess what? My 5 kilogram mass has a bigger force of gravity. So really, I should have drawn it way bigger. Okay, you know, something like this. But honestly, it doesn't really matter because those two forces are going to cancel out. But that's why I didn't do a great, perfect job on my FBD, but it should make sense to you. Okay? Does everybody follow that okay? All right, so now the next step is going to be to draw or to write your equations. So let's write our equations for the 5 kilogram mass. And again, I'm using my colors. So the perpendicular equation would be Fn minus Fg, and that would equal 0. Now remember, is Fn always equal to Fg? No, I hate that word always. When you start using that word always, you are trying to memorize. In this case, do you understand why Fn equals Fg? Well, the answer is those are the only two perpendicular forces, and it's not going to accelerate perpendicularly, so this has to be equal to this, hence that equation, okay? If you like, Fn is going to equal to mg, which is going to be equal to 5 times 9.8, which means Fn is going to be equal 49 newtons, okay? My parallel side, okay, now this is super duper important that you write equations that agree with each other. Well, this is accelerating to the right, so if I write my equation, this has to be Ft minus Ff equals m, I'll call it like m1a, okay, where I'll call this like mass 1. Mass 1, okay. For this guy, my equation is going to be, well, which way is this guy's accelerating? It's accelerating down, so my equation is going to be Fg, and I'll call it Fg2, just so I don't get confused with over here, minus Ft equals m2 times a. And then, now we have to do, you know, if I was to plug in my numbers, you would say, well, geez, I don't know enough stuff. Okay, so I would have to, then I have two equations and I'd have to solve a system of equations. Honestly, I don't care how you solve the system of equations. I just want you to be able to do it. But I want to show you something. If you always solve it this way, it makes it pretty simple because stuff cancels out. Okay, so does that really, you know, FBD and then my equations, and now we got to solve stuff. So let's go about solving it. One more thing though before I finish. It is super duper important. A really common mistake that I get is I'll get students write Ft minus Ff and then they write Ft minus Fg. Okay? Make sure it makes sense to you why that doesn't make sense. If this is accelerating this way to the right, this has to accelerate to the down, or to the down. So these two equations have to agree with each other. Okay? Everybody so far so good? All right, so I want to show you then how I recommend solving these problems. I recommend that you let's write the two equations right on top of one another. Equals, this would be 5 times A, and then this would be Fg2 minus Ft equals 2 times A, okay? Now, here's what I would recommend. If you write the two equations right on top of one another, you could just add each side together. Why? Because these A's have to be the same. Why? Because the things are connected. So the rate that this is accelerating is equal to the rate that this is accelerating. And these FTs have to be the same. Why? Because of Newton's third law. Okay, so if I write them right on top, you'll notice my FT, I get FT minus FT. Hey, that goes away. I know, that's pretty nice. So I end up with FG2 minus FF equals 7 times A. And then I can plug my stuff in. So this would be 2 times 9.8 minus, remember, FF is going to be mu Fn, which is going to be 0.1 times 49, which is going to be 4.9. Okay? And then equals 7a. 2 times 9.8 is 19.6 minus 4.9. And I get 14.7 equals 7a. So a equals, divided by 7, 2.1 meters per second squared. Now, the direction of A depends on which object we're talking about. If we're talking about the 5 kilogram mass, it's going to the right. If you're talking about the 2 kilogram mass, it's going down. So I'm just going to kind of do like one of these guys just so that I know, hey, it's accelerating that way. Now, how do I solve for the tension? Well, I can take and plug 2.1 into here and solve for the tension. I can take 2.1 and right here and solve for the tension. And in fact, if you plug it into both spots, you should get the same number, which is nice because that means that it's always going to work out. So you can always check your answer to see if you did it right. So let's do that. Why don't you do the same? So I'd get 19.6 minus that answer, and I get Ft to be 15.4 newtons. I was when I plugged it into this one. Let me plug it into this one and make sure I get the same thing. 5 times 2.1 plus 4.9. Hey, look, I get the same thing. That's pretty cool. Okay, but that's how you basically solve these problems. The other thing that I want to mention to you, okay, is every problem going to look like this? No, of course not. Okay, sometimes you might have a problem where it's on an incline, going over like that. Okay, but you do the same steps. Draw your FBDs, figure stuff out. Okay. These problems are actually, if you have a problem where it's like this, where you have something like this, these are actually called an Atwood problem, named after an English mathematician named George Atwood. I believe it was 1784 who came up with this type of problem. These problems are way, way easier. Why? Because if you look, this one would just have Ft, and if I call this FG1, and then this one would have like FG2, and then Ft, and then you would write your equation from those two. But again, it's super duper important. If this guy is accelerating up, Ft minus Fg. If this guy is accelerating down, Fg minus Ft. Okay, and then you plug your stuff in and solve. And now it's your turn to practice. Bye, kids!